Chapter 10, Material Properties. The questions that we're going to answer: what are the four types externally of applied forces? What is the difference between stress and strain? What is shear stress? What is a mechanical property? And what kinds of destructive testing methods are materials put through, and what do these tests reveal? Introduction. A physical property is any aspect of a material that can be measured or perceived without changing its chemical identity. Deformation is a change in dimension that is caused by the application of force, pressure, heat, or any other physical phenomenon. Deformable body mechanics. Engineers design structures and mechanical components to perform specific functions. However, a building cannot serve its function if it cannot support its own weight, and the weight of its occupants, or stand up to natural forces such as wind or snow loads. Deformable body mechanics is concerned with the deformations of solid bodies as a result of externally applied forces. Types of externally applied forces. A force can be thought of as a push or a pull. When an external force is applied to an object, it is transferred to as a load. Engineered objects are designed to withstand specific types of loads such as tension, compression, or torsion. Tension results when two forces pull on an object in opposite directions, causing that object to stretch. Compression results when two forces push on an object in opposite directions, causing that object to compact. Direct shear occurs when two offset forces act on an object in opposite directions, trying to split the object in two along a plane that is parallel to the direction of those forces. Torsion is a rotational effect that occurs when two forces, separated by some distance, act on an object in opposite directions, causing the object to twist along its longitudinal axis. Stress. Stress is a reaction that occurs within an object that provides resistance to dimensional changes brought on by applied loads such as tension, compression, shear, and torsion. Uniform stress will occur in a structural member that has a constant cross-sectional area and experiences a normal force such as tension or compression. Uniform axial stress, S, is defined mathematically as the intensity of a normal force per unit of cross-sectional area within a structural member. The common unit for stress is the SI system is the Pascal, although it is such a small unit that megapascals or gigapascals are often used instead. So the formula is uniform axial stress equals the normal force divided by the cross-sectional area. It is important that the concept of stress not to be confused with the concept of pressure. Pressure represents an external load, wherein a force acts across an object's surface like the wind blowing on a sail. Stress is a type of internal pressure that forms as a reaction to an external load. Given a constant load, the amount of stress that builds up within a structural member will decrease as the cross-sectional area of that structure increases. Spreading a force out over a larger area will result in less force per unit area and therefore less stress. Deformation versus strain. If a 10-inch long plastic rod is subject to tensile force that stretches it to 11 inches, then the resulting deformation is a change in length, in this case equal to 1 inch. A change in length that results from compression is recorded as a negative value because the object is decreasing in length. So if it's stretching, it's positive. If it's compacting, it's negative. Strain is also called unit deformation. Is how much a material deforms for every unit of original size. Tension and compression result in axial strain, which is mathematically defined as the change in length divided by the original length. The unit of measurement for axial strain is millimeters per meter. Strain values, and here's the formula right there, strain values can be very small, especially for metals. They are often represented in engineering or scientific notation as a percentage. Engineering stress-strain diagrams. A force displacement is a graph that shows the relationship between force and deformation. Engineers communicate the force displacement test results of standard size material test samples in a form that is applicable to design of any size. The original cross-sectional area and the original test length, also called the gauge length, of the test sample, force and deformation values are converted to stress and strain values. When plotted on a graph, they form an engineering stress-strain diagram. There's an example of one. The curve on an engineering stress-strain diagram is based on a test sample that is a constant cross-sectional area up to the point of fracture. So here on the y-axis we have stress, and on the x-axis we have strain. Elastic deformation. Elastic deformation is the change of size or shape of an object under applied load from which the object will return to its original dimensions on unloading. For most engineering materials, such as metals and plastics, the relationship between stress and strain starts off as a constant ratio, resulting in a straight line from the origin to a point known as the proportional limit. The point is named because, after this, the proportionality between stress and strain no longer exists beyond it. The slope of the engineering stress-strain curve within the elastic region of the graph is called the modulus of elasticity. The modulus of elasticity can be found by dividing a change in stress by the corresponding change in strain. Modulus of elasticity is measured in megapascals or gigapascals. And then there's the formula there. Modulus of elasticity equals change in stress divided by change in strain. The point on an engineering stress-strain curve beyond which a material will begin to experience measurable permanent deformation is called the yield stress. Few materials have yield stress points that are easily identified on their engineering stress-strain curves. It is necessary to use a standard mathematical process called the offset method to determine an arbitrary yield point on a stress-strain curve. The process involves drawing a line parallel to the linear portion of the engineering stress-strain curve, beginning at the 0.002 inches per inch strain value, or 0.2%, on the x-axis. The point where the offset parallel line crosses the engineering stress-strain curve is known as the offset yield stress. Factors on safety and allowable stress. If a component is intended to return to its original geometry on unloading, then the yield stress of the material from which the component is made will usually serve as the actual stress limit. The engineer will decide on an allowable stress limit within the elastic region of the material's engineering stress-strain diagram to ensure that the design will avoid structural failure from situations such as accidental overloading. The ratio between a material's actual stress limit and its allowable stress limit is referred to as its factor of safety, or N. So then you can see N equals the actual stress limit divided by the allowable stress limit. Factors on safety vary depending on the application. Some factors of safety are dictated by codes, which are standards that are enforceable by law. The geometry of the structural component along with the allowable stress can be used to calculate the maximum allowable load. Allowable stress equals the yield stress divided by the factor of safety. Plastic deformation. Plastic deformation occurs beyond the yield stress and continues to the point of fracture or total structural failure. Ultimate stress, which is the maximum amount of stress the material can withstand without failing. Beyond this point, the material will exhibit necking, which is visible decrease in cross-sectional area at the location where fracture will eventually occur. Percent reduction in area and percent elongation. Percent reduction in area is a measure of the amount of necking that occurs in a tensile test sample at the cross-sectional area where fracture takes place. The formula is percent area reduction equals the original area minus the final area divided by the original area times 100. The percent elongation is a measure of the amount of stretching that occurs within the gauge length of a tensile test sample. Percent elongation equals the final gauge length minus the original gauge length divided by the original gauge length times 100. Shear stress. Shear force, V, generates a slicing action through the material as a result of shear stress, tau. Shear stress equals shear force divided by shear area. Mechanical properties of materials. Mechanical properties are attributes that all materials exhibit to some degree when subjected to external forces. Properties include brittleness, ductility, elasticity, hardness, malleability, strength, and toughness. Strength, ductility, and brittleness. Strength is a general term that refers to a material's ability to resist applied loads. Ductility is a term that describes a material's ability to experience plastic deformation through tension without breaking. Brittleness is a mechanical property that causes a material to fracture at relatively low strain values. Malleability, elasticity, and hardness. Malleability is a mechanical property that allows a material to experience plastic deformation through compression without breaking. Elasticity is a mechanical property that allows a material to return to its original dimensions once its load has been removed. Hardness is a mechanical property that gives a material the ability to resist surface penetration, scratching, or wear. Toughness. Toughness refers to a material's ability to absorb energy that results in permanent deformation. Answer the following in your engineering notebook. How are the externally applied forces generated? How do stress and strain relate to a material's modulus of elasticity? Why would an engineer who designs structural components be most interested in the elastic region of a materials engineering stress-strain diagram? Why do engineers apply factors of safety to their designs, and how do they use them to determine allowable stress? How is shear stress generated? What kinds of mechanical properties do materials exhibit? Why would an engineer be more interested in using an engineering stress-strain diagram over a force displacement diagram when comparing different materials? What is the difference between elastic and plastic deformation? Identify a situation in which an engineer would want to establish an allowable stress for a component that is part of a mechanical system. And who is responsible for the development of materials testing standards in the United States?